from Hungary, I guess. Yeah, we'll reviewing the whole stage at the end.
Yeah,
so
like
still, the last couple of people are going down the stairs to meet their seats, so we'll wait a few seconds. Please come in. And yeah, everyone's here, so please start your preparation of the report, 5 minutes. The report on single lens telescope. Please, is the microphone working? Is it better now?
Hello, testing.
Okay, so now, please.
Okay, so hello everyone, I'm reading from Team China, and today I'm going to do the report for problem number 3, single lens telescope. And let's first reveal the problem. A telescope can be built using a single lens, provided a small aperture is used instead of an eyepiece. How do the preemptor of the lens and the hole influence the image? So the problem asks us to investigate the preemptor's influence on the final image. And we primarily consider this preemptor, the photo lens of the lens, and the LD lens of the telescope, and lowercase d, the diameter of the pinhole, and the uppercase d, the diameter of the lens. So here's my content for today. We will go through the preliminary experiment to introduce the setup and key working principle and the phenomena of the single lens telescope. Then in theory and experiment part, I will split my investigation into preemptor influence on the image's magnification, resolution, sharpness, and brightness. So here, first let's view our preliminary experiments. We first use the paper cone and the aperture whose diameter can be changed from 0.6 mm to 2 mm to make the telescope with adjustable lens to view distant object. And here's the phenomenon that we observe. The first picture is the original picture that we shoot it without the pinhole or without the telescope, and the second is only with the lens. We can see that the second picture is actually has some magnification, but it's very blurred. But when adding a small pinhole, the image compare. But when we only have one pinhole, the image remains the same. And we just found that with the pinhole, the magnification is actually the same. So from the phenomenon that we can have a positive working principle for the system. Consider a distant object and image through the convex lens. A real image S1 will form near the photo lens. If we want to obtain a higher magnification, or say if we want to have a bigger picture, we need to put our eyes nearer to the S1. So the objective lens and the position of the eye determine the magnification. But human eye and most camera lenses cannot focus on objects that are too close to them. So like most far-sighted people, the image is behind the retina. So a point will image as a spot on the retina, which makes the image unclear. But if we add a pinhole to restrict the angle of the incoming beam, the spot gets smaller and the image will get clearer. Meanwhile, the brightness is also restricted by this pinhole since this beam came into the eye. So the pinhole acts as decided the quality of the image and the brightness of the image. So now we have clarified the aperture and the pupil of the system. Pinhole obviously acts as the aperture stop, so restrict the light beam, and whereas the lens is the field stop, restricting the field of view. The hole is also the active pupil. So now let's move on to a theory and experiment. First is the angular magnification. And we adopt the angular magnification because people see things as being large or small, not because their actual size, but the angle of view, which is the angle at the pupil subtended by the object. So strictly speaking, one should take the tangent of that angle. And according to some simple geometric calculation, we obtain that the angular magnification equal to object distance v over v minus L, the length of the telescope. And the object distance approach infinite, the way approach f, and the angular magnification approximately is f over f minus L. So through the equation, when L is larger than V and V is negative, the upside down image occurs, and when L is less than V, the MV is positive and upright image occurs. So of course, in actual experiments, we use much more accurate devices to ensure that coaxial and avoid error. This is a lens and this is a small hole, and we use the camera as a receiving device. So the magnification is measured by shoot the picture of a distant object, first shoot directly through the test tube, use the software to measure the object height, then shoot without the telescope. The ratio is the magnification, as the picture shown. And here's our experiment result. Here are both the positive and negative magnification. Both are well agree with this directional line. And when the pinhole is closer to the photo point, larger the magnification. We did another 3 set of experiment, changing the diameter of the aperture and the photo length separately. The result is the photo length increases, the magnification decreases, and the pinhole diameter does not affect the magnification. So now let's move on to the sharpness and resolution. First is sharpness. Sharpness is defined as a gradient of gray value in the edges of the image. So this is more steep, so the sharpness is higher, and this is sharpness lower. And sharpness is decided by both the contrast of the light intensity and the spatial resolution, which represent the scatter of the single point on the object. For example, caused by the diffraction or else. So sharpness is correlated with such a ratio. So in each experiment, we use a board car with line pair and record the final image using camera, and we use Mathematica to obtain the gray level distribution and calculate the sharpness of the image. We can calculate sharpness from this image. And here's the result we get. We changed the diameter of the pinhole and found that the sharpness is first increased, then decreased as the pinhole diameter increased. So notice that sharpness has a correlation with both contrast and angular resolution. So we separate these two values. First is contrast. We changed the pinhole diameter and found that the contrast doesn't change much. So there must be something about the angular resolution. The angular resolution is due to both the geometric limitation and the diffraction limitation. The pinhole itself, consider point source, will go through a pinhole with radian. The image is a disk instead of a point. The geometric limitation can be written as this. And simply consider the related criteria, we can write the differential limitation as this below. And we found that the first is inversely it's proportional to D, and the second is inversely proportional to D. And if we plot these two lines and simply have the maximum of the limitation, and we can get the exact diameter value for the resolution. Of course, this is a wave point source is spherical wave after the convex then and going through the pinhole. So diffraction cannot be simply the Hopf diffraction. So we use Fresnel-Kirchhoff diffraction formula to calculate the actual diffraction spot. And this is both contain the geometric limitation and the diffraction limitation. So this is a diffraction spot we get, and we can see that it's hard to have a criteria of the width of spot. So we have definition of the spot underside the angular position of the trough of a first peak whose intensity is larger than 0.1 of maximum peak intensity. Well, this definition is of course very complicated. It just means that the ring that we can see the light spot. So to make it more clearer, we have a graph. This is the Hopf diffraction, and this is the actual diffraction. This is a related criteria, and this is the geometric limitation, and this is our criteria. So in an experiment, we use a point source created by a sodium wiper lamp and a 0.5mm pinhole. And we change the pinhole diameter of the single lens telescope and the distance between the image and the pinhole. So this is a result we get, and this is a simulation of the numerical solution that we get from our Fresnel-Kirchhoff calculation. And we can see the similarity between these two. And the blue line representing the related criteria. The red line is a geometric limitation. The dark line is dark point is a Fresnel-Kirchhoff formula, and the green point is our experiment. We can see there is the agreement, and we can see that a related criteria and the geometric limitation can approximate the real image of the point. So this is the thing that the sharpness is first increased and decreased because the angular resolution first decreased then increased. Now let's move on to the brightness. For the luminance, we can see that from simple calculation, luminance is only correlated with the system transmission coefficient and has no correlation with any parameters. But the brightness of the image we saw is actually the subjective luminance is at the illuminant on the retina. Since the human eye pupil is larger than the pinhole, so we can know that the illumination is proportional to the square of the diameter of the pinhole, and it's equivalent to the diameter of the lens. To do the experiment, we shoot some picture and try to get the grayscale, and we found that grayscale is actually proportional to the illuminance of the picture, and this is our Tabor line. And for experiment, we use a sodium vapor lamp as its intended source and take photo of it, and change the average grayscale to average luminance. And here's the result we get. We can see that the result is coincides with the theory that the luminance is proportional to the square of the diameter of the pinhole. So in further insights, we use the Fourier optic view to see the system. First is the point square function. A point square function is how a point can actually image through the system. And we can see that this is simulation result from the VMAT software, and this is the calculated result from our first new turtle calculation. And we can see that these are very similar. And secondly, modular transform function. Modular transform function is how the system reacts to certain spatial frequency. And if there is a high frequency index, then the picture is clear. If the high frequency portion is lost, then the image is blurred. We can see that the blue line is without the pinhole, and when decreasing the pinhole diameter, we can see the high frequency component is adding into the system, and we can see the image became clearer. So now we draw our conclusion. For the angular magnification, the photo length and the total length of the telescope is correlated with it. And for the resolution, the most important is the pinhole diameter, and both the photo length and total length influence on it. And the pinhole diameter only influences the brightness only influenced by the pinhole diameter. So we can see that objective lens is the main magnifier, and the pinhole is the after stop or high pass filter, which can make the picture more clearer. And magnification, we can see the MA equals to F over F minus L, and there exists an upside down image and the upright image, and when F is larger, the MA is smaller, and closer the pinhole to the photo point, the larger the MA is. This is verified by our experiments. And also the sharpness, first increase then decrease, and contrast remain the same, and resolution for decrease then increase. So the resolution can calculate by first near Kirchhoff diffraction formula. And brightness is in proportional with D square. And further inside, we can explain this phenomenon in Fourier optic. And here's our references. And thank you.
Thank you very much.
Thank you for the report. So my first question to the reporter, on slide 25, what is the distance between the object and the telescope in this photo? Yes. What's the distance between the object?
It's about 10 meters.
10 meters.
Yeah.
So do you think this is sufficient to approximate the object at infinity?
I think it's sufficient.
Okay. So on slide 19, I can see that the object is blurred in this photo. So how do you accurately determine the magnification when the image is blurred?
This is just an example picture. In actual experiment, we use the light gun.
So is the image blurred when you measure your magnification?
We use this, and we can measure the distance between this, and the blurriness has a little effect on the magnification.
Thank you. So on slide 27, how do you determine the angular resolution of your telescope?
You mean this?
The angular resolution.
No, this is sharpness. This is sharpness.
Yeah, how do you determine the angular resolution?
This is sharpness, not the angular resolution.
So did you determine the angular resolution?
Yes, in the next slide.
Okay.
Sorry.
So do you use coherent or incoherent light in your experiments?
We use incoherent light.
Okay. So is your system focused or is it defocused?
Well, you can see that from different points. If you see that on the retina, it's an in focus. But if you consider the pinhole as an ideal pinhole, then it's focused.
Okay. So on slide 31, would you consider this as the Fraunhofer diffraction pattern?
Yes. No, I don't think so.
So what is this diffraction pattern?
This is the calculated result about Fresnel-Kirchhoff diffraction formula.
Okay. So in the Fresnel-Kirchhoff integral, did you consider the effects of the telescope and the eye lens?
What? Sorry?
Okay, never mind. Did you model your camera as a thin lens?
What? Thin lens, yes, we consider the thin lens.
So how do you calibrate your camera to obtain your luminance values?
Oh, yes, we have an actual PowerPoint for it. Actually, we have a point source in here, and without telescope, of course, we shoot the picture from a distance, and this intensity of the light source can be controlled through electronic current, and we change the current and shoot the picture.
Okay, thank you very much. The time is over. And time for preparation for the opponent, please. 3 minutes.
I'll be providing an opposition on problem number 3, single lens telescope. So first, I'd like to give a summary of the reporter's report. So the reporter had geometric ray tracing to calculate the angular magnification by assuming the object to be located at infinity. Furthermore, the reporter gave some discussion on the usage of the Fresnel-Kirchhoff integral to predict the angular resolution of the telescope and the diffractive limits, and also provided some intensity predictions and measured them by calibrating the camera intensity. So now I'd like to go through some strengths and weaknesses of the report. I felt that the qualitative explanation that the reporter offered for how the single lens telescope actually works was quite clear in the manner that they discussed what the role of the first lens is to produce the real image, and then the role of the pinhole, which is to allow us to be more focused on the geometrically blurred image. Next, they gave a quantitative prediction for the angular magnification using geometric optics, and I feel that over here they did not. And furthermore, they had an experimental investigation of the angular magnification with their optical bench, and they placed the object sufficiently far away to a proximity as infinity, and I felt this was commendable. They also talked about their forward optics simulation, which they claimed could provide some predictions on the image, on the diffractive blurred image. However, I'd like to talk about some areas of improvement for the report. So firstly, I'd like to talk about how there's no predictive power for how the image actually looks like when it is blurred through diffraction. So we understand that in a single lens telescope, there are two types of blurring for the image. At large pinhole sizes, the image is geometrically blurred because the real image that is formed by the single lens is very close to the viewer, and this cannot be focused on. However, as we decrease the size of the pinhole, there will be a trade-off between the reduction in the geometric blurring due to the aperture cutting off the spread of rays, and also the introduction of diffractive blurring due to the small aperture size approaching the wavelength of light. And I thought that they could not predict what the image actually looks like when it is diffractively blurred using the Fresnel-Kirchhoff integral. Next, there was no consideration of vignetting due to some effects. So firstly, I think the thickness of the pinhole is rather significant because if the pinhole is very thick, that light rays can actually reflect off the inside of the pinhole, and this could create an intensity fall off near the edges of the image. And there was no actual intensity image prediction given by the reporter, and there was no verification experimentally. So this is something I'd like to discuss later during the discussion. Next, there's no predictive power for the transition regime. So what I mean is that the reporter simply combined the theory for geometric blurring based on the ray tracing theory, and then they included the prediction of the Fresnel-Kirchhoff diffraction integral, and then they simply solved for the intersection between these two theories. And I believe that this is not accurate, as it does not properly account for the transition regime when we are transitioning from geometric to physical optics. And I think that one way this could have been accounted for is by using Fourier optics, and this is something that was not discussed very in-depth in the report. So again, this is another thing that I'd like to be talking about in the discussion. So again, the Fourier optics theory, I believe that there was no real discussion on this, and I think that Fourier optics is actually a very powerful tool to help us predict several properties of the single lens telescope system. For example, it will give us predictive power over the actual image, and the reporter showed some images that they predicted. However, it is not very clear how they derive the point spread function that they use for their Fourier optics. So I would like to discuss that later in the discussion. There was also no discussion on how this Fourier theory can allow them to optimize the system for the optimized pinhole size, which will occur at the transition regime between geometric and physical optics. So now I'd like to invite the reporter up for discussion.
Okay, thank you. First, I may make some clarification of our theory. First, I didn't use the infinite closure, the approximation, because in the final calculation, we use F because it is more clearer, but in the calculation and the theoretical line, we use V, the object distance. So we didn't actually have the infinite approximation. We use the object distance and the calculate the image distance. So we didn't use the and second is the first curve of calculation. I first show a diagram. Sorry, I cannot reach it. And this is first the diffraction pattern, and I believe this is a geometric detection. I said this is an inaccurate prediction of the actual.
Yes, I agree. This is inaccurate.
So I use Fresnel-Kirchhoff calculation. And do you know Fresnel-Kirchhoff calculation actually can approximate, can include both geometric and physical.
I agree.
Yes. So why do you think that Fresnel-Kirchhoff calculation could not predict the relation between the physical optic and the geometric?
Okay. So one thing I'd like to clarify is how exactly you calculated your Fresnel-Kirchhoff integral. So I know that there's there'll be, sorry, can I have this? There'll be an object plane, and then there'll be a pinhole, and then there'll be an image plane. And you simply use the integral to calculate what the change in what the image is based purely on the effects of the pinhole. Am I correct to say this, or have I misunderstood something?
You can see that, but
okay, so we understand that in the single lens telescope, because of the lenses, the first lens and also the eye lens, and the fact that the system is defocused because the real image is too near to the eye, then the image will actually the focus image will actually not be at the retina plane.
So you said about the defocus phenomenon, but actually defocus or focus doesn't influence the practice of the calculation, because if we consider here as a length and as here is a hole, and we use the end plane not just not behind it but in front of it, because our eye also has a lens that can actually focus on the retina.
I disagree with this because I think that when you perform your Fresnel-Kirchhoff integral, you have to account for the phase shifts due to both the lens from the single lens telescope as well as the eye lens. And because your integral is very simplified, it cannot account for those phase shifts. This will result in the defocusing.
My apology. I didn't explain that clear. I didn't use the lens to do the Fresnel-Kirchhoff. I use the object to have the image from the lens. So actually, I use this image to have the diffraction formula from this pinhole. So actually, I use the image and the diffraction frame is the pinhole, and I use the spring as the infinite.
Okay, so what I understand is that you first calculated the real image that is formed by the first lens, and then you applied the Fresnel-Kirchhoff integral and the diffraction effect due to the pinhole. So one question that this raises to me is, let's say the object is here, and the lens is here, and the real image formed by the lens is behind the viewer and is behind the pinhole. So how would you deal with this?
Because the human eye actually has a lens. Don't forget this.
Yes.
So actually, if you can have a clear image, it means it has a clear image in your retina. Your retina, maybe the spot, the point spread functions actually calculate how this spot actually diffuse. So actually, this formula calculates how this spot actually can diffuse. If you consider ideal pinhole so that only one beam can come through, then there is a clear image in your retina. Do you recognize that?
Yes. What I'd like to point out is that the single lens telescope will always be a defocused system, and it's the addition of the pinhole.
Do you consider a small hole, a single small hole? Sorry, can I borrow this?
Yes.
Organizers, can we have more pens for the thank you very
much. So do you consider an image here and a pinhole here and the image here as not focused?
Yes, I think that because
so
the image.
You consider the pinhole actually don't form an image. So why do we say the pinhole image?
The pinhole does not form an image. I think that the focused image that is formed by the single lens telescope is not at the retinal plane, and therefore the single lens telescope.
But actually, even if it doesn't focus on the retinal plane,
okay,
I can still calculate how the pattern looks through this image, the real image formed by the lens.
Yes, you can calculate the real image, but you cannot calculate what the eye sees because these image planes do not align. So allow me to move to my next point, which is regarding the Fourier optics.
I still disagree with you, but
Yes.
I can move on.
Okay, we can agree to disagree, and I'd like to move on to my next point, which is regarding your Fourier optics theory. So can you tell me how you derive the point spread function for the Fourier optics? Because I know that the point spread function determines how a single point what will a single point form on the image plane when it passes through your
I know what
system.
you're saying, and this is done by the Lightress software, the Max, and it can simply you calculate the lenses and the pinhole here, and have a simulated eye here, and you can have the point spread function on screen. Yeah.
So the point spread function will determine what the image looks on the image plane. So can you draw for me, if the retina is here, this is the retina, where is the focused image plane that your point spread function is predicting?
It's on the retina, and this focus can be adjusted. It's set on software that can be adjusted to 25 centimeter to infinite. That is just as our eyes can. Or we can calculate optimize the image in the plane. So this is the point spread function on the retina.
So can you show us some of your predictions from the Fourier optics theory?
You mean the
So did you attempt to verify any of these predictions? Did you attempt to verify the intensity profile from your Fourier optics prediction?
Sorry, not it. Sorry, wait a moment. Sorry.
It's fine if another team
You can
member.
continue your question.
Yeah, so what I'd like to ask is, so I understand that for Fourier optics, the point spread, you basically
Okay,
have to
this is the
perform...
point spread function that our simulated software had calculated for us, and this is a first order of calculation that
So
we
can you
have.
tell me what is the physical significance of... Can you tell me what is the physical significance of the point spread function, and how does this allow you to obtain the image?
Okay, the point spread function. I'm sorry, I didn't have this. It's a point source image to a system, and this system is the singular telescope, and our eyes and the camera image is on retina. So it's called a single point will image as a spot. So if a single point image as spot, then we will see the image as blur, and our annual resolution can actually form by this blur. Just like the Rayleigh criteria and the iris, if these two spots are too close together, and we can see this clearly because they are two spots.
It seems there's a problem with the mics completely.
Yeah. So I believe that the point spread function, if you are correct when you say that the point spread function determines what a point will look like on the image plane after passing through the system. And what we have to do is we have to convolve the point spread function with the object intensity. So this means that we multiply the point spread function on every point on the object, and then we can calculate the resulting image.
Yes,
and this
of
is
course.
fundamentally what Fourier optics allows us to achieve.
Yes, of course that can predict how the one image looks, but we are trying to define the annual resolution of the system.
So did you attempt to experimentally verify this?
Verify the
This
actual
image that you see here.
what's the image I see here? It's just 2 points.
So did you experimentally
Yes,
verify
and
it?
of course determining and verify it. It's sorry.
So I believe that you have not been able to provide me a convincing experimental verification.
Convincing?
Yeah, no, I don't think this is convincing because below we can clearly see the center as a black spot. Right?
Yeah, and the simulated result is the black spot. If you consider the Fresnel diffraction, there will be black spot and light spot on the axis of the object.
I don't believe that this is a very
This is
convincing
a very diffraction, so it's actually occur and this.
So, never mind. I'd like to conclude my points on this, and I believe that while Fourier optics is a way of allowing us to calculate the image, I do not believe that you have provided us with a sufficient,
I believe Fourier optics are in sense identical with the field optics, just a different calculated way, but their results are same. So what I don't see the good thing about And if you try to use the word object, could you tell me how? I mean, for this system, which is the object like?
Okay, I believe that for this system, you have an object, you have two lenses, and you have a pinhole.
Wait.
What you can do with this system?
I'm sorry.
This is a
First of all, I don't
summary.
Mics are not working, as you've spotted probably, and we have a lot of cows. First of all, like the time is already for summarizing of the discussion, but we can continue the discussion. So can I have an answer? What about the mics? Can we get them repaired very soon? Okay, so after finalizing the discussion, we just wait for a minute or two if we can repair it, because it's very hard for the jurors and for the audience to get what's going on here. No. Discussion, but you can't continue with the review and everything because it's very hard. Like we have seen something here and got something. So I hope we can have it done very quickly. Any feedback on that?
Poor Martin.
Is that
Any performances?
Confucius said, Espino gets
Joe, please. Okay, so would like to start with Joe. So who was the one shouting out? I see you. I have the light corner, so and you have a good voice enough to tell us the joke. Please, it's your turn.
Give me a second, I'll think of one.
That's
Maybe someone
fine.
else will want one.
The second's gone. So any feedback from the technicians whether we have to wait or there is no chance to get it fixed?
And the radio is down.
even the wired mics are dead.
Probably the amplifier is down.
Amplifier's down.
Maybe for the speaker. That's the worst. That's the worst situation.
Yeah.
Yeah, because
Yeah, just roll a piece of paper here. Oh, the one that Manish
So the
burnt it.
response
Is
came,
it?
and the response says we have no idea how long will it take. So I think in that case it doesn't really make sense to wait further. So could I ask every one of you to be very calm so that we have a chance to hear? Because I don't want to prolong this stage like waiting half an hour for having 1 minute concluding remark of the discussion. But
Yes.
we're testing microphone now. Does anyone have one?
oh, finally. No. Another one. Destructive hands.
Is that also right?
The receiver's problem.
Okay, so back to the plan B. Calm down. 1 minute.
Okay, so now I'd like to give a summary of the discussion that I just had with the opponent. So first formula that she used in her report, and I felt that it was not properly explained in the report how exactly the Fresnel diffraction formula could have been used to predict the image that she actually sees. And I believe that she was not she did not understand properly what I meant when I talked about an unfocused system. And I felt that the only proper way to predict the image of an unfocused system and account for geometric blurring is to use Fourier optics, which she only discussed briefly in the report. So we talked a bit about the Fourier optics theory that she used, and she was unfortunately unable to tell me how she derived several things, such as the point spread function that is used in Fourier optics to convolve with the object to obtain the image. And I believe that she also did not experimentally verify the blurred image, and therefore I believe that well, the reporter gave a very good explanation, or rather a very good investigation into the magnification and also the brightness of the single lens telescope. Due to the limitations of her theory that I discussed earlier, the sharpness was not properly touched on. Thank you.
Questions from the reviewers, please. Please can you share the working microphone?
First, for the opponent, what do you think is the simple physics behind this point spread function?
I believe that the point spread function helps us determine what the resulting image is that a point source forms when it is viewed through the single lens telescope. And if we multiply the point spread function with every single point source that the object comprises of, we can then sum up the result to obtain the image, and this is what Fourier optics achieves.
Okay, thank you. How small was your pinhole?
The pinhole is about at least 1 millimeter. So we use different pinhole, about 0.1 millimeter, 0.2, 0.3, 0.1.
Okay, so you investigated a lot. Yeah. You asked about the thickness of her lens. Do you think her lens is thin enough to be the error of the thickness caused by the lens thickness can be neglected?
I talked about the thickness of the pinhole, and unfortunately we did not have enough time to discuss that. But I believe that the non-zero thickness of the pinhole will result in a vignetting effect, which will change the intensity of the image.
Okay, I'm also sorry for that we didn't discuss the technical pinhole because I also investigated them and they didn't understand that.
This is not your stage.
The optical aberrations. How long was your focal length?
How long was my focal length?
Yes.
We have different focal lengths too.
Which was the longest one?
The longest one was 30 centimeter.
Okay, and you think it's really legible when you determine objects with 10 meters away?
Oh, I didn't use the infinite approximation. I said it.
Yes, for example, the chromatic aberration can be neglected because if chromatic aberration...
Yes, we use a high quality lens. Our lens is about maybe 500 Singapore dollars.
And what do you think is the ideal place of the pinhole?
Oh, the ideal place of the pinhole is the place of the pinhole.
Yes,
it's actually
like in the focal point of the...
no, in the focal point it will be too blurred. So you have to manage between the blur and the magnification.
And so behind or in front of the pinhole?
Behind it will be a upright down picture, and in front it will... so it depends actually on the observer. So if you want a bigger, also larger image, you should be more closer to the focus, but more clear the image, and you should be...
Did you investigate the regional focal point because of chromatic aberration?
Oh, I said
yes
no, I didn't, because our lens is very high quality.
But the errors of the lens also depend on
this very small error, so it's about maybe...
So did you investigate the errors of your lens?
I just investigated in range about 3% distribution error, so I think that's natural.
Okay, thank you, thank you very much. The time is over.
So first about the overview of the report, I think you failed the task by making the telescope consisting of a single lens and a small aperture. But about the lens and the properties of the lens and the whole, you investigated the whole size, focal length, and diameter. But I missed the part when you investigated the optical aberrations and the errors of your lens, because there can be quite a big range of the errors caused by a lens. And is the influence of the image. Like you make measurements for your magnification, sharpness, resolution, brightness. Sometimes it's the errors like chromatic aberration. And I missed that you didn't optimize that for a picture. How can you optimize that? Both brightness, magnification, resolution is the best at the same picture. But like you could do that, you change for the place of the pinhole and you record what you see with the camera and you analyze the pictures and then you could have tried to determine where is the optimum for both for every parameters. And then about the discussion. I liked the speech because it was a brief overview of what the report did. You pointed out several weaknesses of the report, like blurring the thickness of the pinhole and the unclear explanation of the Fourier optics. Like you showed us lots of equations, and there was some variables you didn't define clearly enough, and you talked a bit with the high speeds, so it was pretty hard to follow in some points. And you expressed your opinion in the speech, and it was quite good. And about the discussion, so it was a heated discussion, and in some places it was hard to follow, I must admit. But the opinions were presented in both parts, which is great. And I think, but there was a pretty bad time management. As you mentioned, there was some relevant questions you didn't have time to ask, and you didn't challenge her experimental setup and the errors and how she made experiments. But you let her to explain properly her arguments and her views. So about a topic, you talked about the calculation of the image, and she said she can calculate it sufficiently, and you went into details that islands, the difference caused by the islands can be calculated in. I think this whole thing is a bit overcomplicated, so you should have gone into the simple, basic physics behind this whole phenomenon. But I think you're right, and the islands can be calculated with. And so there were some missing points, like the basic explanation and the reason why you use the errors of your lens weren't calculated with. You didn't show clear relations between the things and the formulas. And about the opponent, you asked about parallel light rays, and that you didn't go further that this 10 meter is a big distance enough. But I think overall it was a great report and a great discussion, so thank you for this.
Thank you very much.
Opponent, and the reviewer. I have a great discussion with you. And now let's have some conclusion. First is our study conclusion. We find that the focal length and the total length of the telescope has effect under magnification, and the pinhole diameter has a decisive influence on the resolution, and also is the focal length and the total length. And the brightness only decided by the pinhole diameter. So some response to the opponent. First, the distance. We didn't use the infinite approximation. We actually calculated the object distance and the image distance and the blur and magnification. We separately measure them. And I don't think it is reasonable for example, you use lens with a variance and there has some blur, and you said this lens magnification is larger because of a blur. I don't think that is reasonable. And the dispersion pattern is the pattern of a point source, so our experiment verified it. And the Kirchhoff calculation is a calculation of a spherical wavefront after the pinhole at infinity. And the Fourier optics are also feasible, but it's equivalent to the interpretation as our physical optic suggested. And the scoring criteria we used to decide the spherical resolution, and the wheel of field we also investigated, but due to the lack of time of discussion, we didn't have time on it. And for the reviewer, since it's a pinhole, we actually discussed it, but for the experiment we use infinite same pinhole. This is a discussion, but we don't think I have time. We use the same pinhole in the experiment, so I don't think that influences much. And the lens we use a high quality achromatic lens, so there will be no chromatic, and the aberration is small. So the aberration is actually depends on the quality of the lens, so we need that in our case. Thank you.
Thank you very much.
Okay, a few short questions to report. What is B on your slide 41?
Oh, B is the image listen. I believe, I don't know.
B is image what?
The image listen from the lens. That's the opposite.
Distance.
Okay. Your slide with references mentions a few papers by M. Young in American Journal of Physics, in Applied Optics. Can you tell me what parts of your theory are taken directly from these
Actually,
references?
no.
No.
Because it is a basic study on the pinhole camera, and our system is a pinhole telescope, so the basic concept is wrong, but I have some.
So no parts of it.
Yeah.
Okay, good.
Last one?
Yes, the last one. What is new on your slide 33?
33. Sorry, I can't connect to the.
Okay. It jumped over from the mics to the computers.
33. It's 33. Or 43. 33.
There is a large integral.
Oh, yeah, that's the first year Kirchhoff interval.
Say again? Kirchhoff interval.
Yeah.
Okay, thank you.
Okay, thank you. Tomasz, Tina, could you pass on the mic? Thank you very much.
Thank you. Question for our teams. What parameters of the lens do you think will influence the properties of the image?
And a very brief answer from all of you, please.
For me, the diameter of the lens, and also, of course, if we take into the focal lens, and if we take into the variation, we can also see the material or the quality of the lens. But I didn't consider it because our lens is high quality.
Opponent?
I believe that the diameter of the lens is very important in determining the field of view of the object. And I also believe that the focal length of the lens will help us determine where to place the pinhole to see the maximum angular magnification, as well as where the image will be inverted.
Okay, thank you. And the reviewer?
I agree with the diameter, the focal length, and I think the aberration is important because it determines where to put the pinhole and the refractive index.
Okay, thank you. Unless other jurors have questions, then Ilya, please.
A short one to the order, please. On your slide 20, what is first, second, and third experimental groups?
Oh, okay. This is both on the under magnification, and we first change the photo length of the lens, and then change the diameter of the pinhole.
Groups of what?
Group of experiments. Sorry,
So what does it mean? Why are the experiments divided into different groups?
The variable in the graph are the length of the telescope. So we fix the photo length of the lens and the diameter of the pinhole, and change the length of the telescope, and do 3 or 4 sets of experiments. Thank you.
Okay, John.
Thank you. Quick question for the reporter. Can you just explain what is meant by achromatic lens?
Achromatic lens is it's through a combination of the two different refractive index lens, and it can degrade the effect of the chromatic.
Well, you were using monochromatic light, so does that
Yeah,
important?
that's important, so I don't think that's important. I'm only using sodium vapor, so I don't think that's important.
Okay, thank you. Further questions? It seems no, because jurors are already using this time for filling up the sheets. So thank you very much for your appearances here, and now we have time for.
By asking. Yeah, I don't know. Not sure.
Please, we'll be ready in a few minutes. If you could still keep sitting on your places and staying calm, because we also working here now and need some reasonable atmosphere to do that. Jurors are performing precise measurements of the weights of the criteria. So. So it seems everyone's ready. Can I see the grades for the report? No. It's an 8, 9, 7, 9, 7, 8, 6, 6, 8, 7, and a 7. Thank you very much. Grades for the opponent. Now, 7, 8, 8, 9, 8, 9, 6, 7, 8, 7, 7. Thank you. And grades for the reviewer. Now, it's a 5, 7, 6, 6, 6, 7, 6, 6, 6, 7, and a 6. Okay, so for the report, we had twice a 6 and a single 9. So, Ilya, would you like to make a few short comments on the 6?
Okay, so your report was obviously a very good report, and it was above average on my scale as well. I liked that the fact that you had many experiments performed, and your theory was interesting, but I could not go towards the higher end of the spectrum for many reasons. First, I had a real problem with how you set priorities in your solution, because I thought that you spent too much time, you devoted too much attention to some of the aspects of this effect, on how to build a pinhole camera and how to build a single lens telescope that were more or less known in literature. So your contribution, your own contribution towards going further and building something new was somewhat limited, in my opinion. And therefore, in the criteria that concerned setting priorities and bringing your own novel contribution, as well as citing sources properly, I could not add you many points. And as for the partial grades, my partial grade for the report itself was 2, and my partial grade for your discussion with the opponent was 3. I think that the discussion was nice and productive, but I could not go much higher due to the fact that you interrupted your opponent on many times, and also I had an impression that the points that you tried to explain to your opponent were a little bit irrelevant. They were correct, they were perfectly reasonable, but they were somewhat irrelevant and not the key points that would reflect the essence of your solution and your important contribution to solving this problem.
Sorry, can I clarify that I didn't reference any of the criterion in the references. This reference is just the reference print, and I saw them and I saw all of them are wrong, so I gave up all my theory in my own.
Yeah, that's the game. We have many jurors here, so some of them might have different opinions. Yeah. So sorry for that, but yeah, we have a 9 here. Oh, actually, we have 2 of them. Yeah, we have 2, but like, could you comment on one of those?
Okay, I thought you had a really good, you did a good job explaining the phenomena, and I was impressed with your modeling, and I thought you showed great understanding of this phenomena in the discussion. And so I gave partial grades 4.5 for the report, 3.5 for the discussion.
Okay, yeah. So that's the interview. For the opponent, back to Ilya again, a single 6 there.
Okay, so this grade is related to the grade for the report. I felt that in the discussion part, you were also interrupting your reporter and not really reacting to her answers. So in my opinion, the discussion was good, but it could have been better, and you could have earned 4 points from me concerning the discussion and how you led and directed the discussion and how you set priorities in the discussion. And as for the essence, the scientific essence of your opposition, I again felt that the points that you were raising were correct, reasonable, but some of them were not very much relevant. So some of the points that you were discussing were just basic optics, and therefore, as for the partial grades, my partial grade for your for the essence for your presentation was 2, and my partial grade for your discussion with the reporter was 2 as well. So that's why I ended with a grade of 6 for your opposition.
Okay, thank you very much. But again, we had twice a 9, and one of those was or Elia. Would you like to? Okay. So Daniel. Okay, Daniel. Okay.
Okay, yeah, it's already high with my grading for the report, and therefore went up to a 9 for the opposition. But basically, you had good questions at the beginning, so I gave you 2 points in that section. Then for your opposition discussion, it was mentioned that you only went into 1 point, but I thought that this point is what you could do and what you should do, and therefore I gave you 3 points in the 2 other parts, and then the other, which was 9.
Okay, Elia?
I don't think that the opposition of finance and only they raised the point of the diffractive limit, which is a very good point, and so overall it was a good opposition with very relevant points. That's why I gave 3.7 for the speech, 3.3 for the actual discussion.
Okay, thank you very much. And coming to the reviewer, it's pretty consistent in having a lot of 6, 3 7s, and a single 5 for myself. Sorry for that. So basically, yeah, my partial grades were 1.5 for questions, 1.5 for the review of the report, and 1 point for the review of the opposition. Basically, what I felt it was the, let's call it a standard IYPT review with no big pluses and no big minuses. So I didn't feel that I should deviate too much from the average. So I felt it should be somewhere around between 5 and 6, and somehow I felt that the part of the review which was touching the opposition was a little bit weaker. So then I decided to go for 5, but it could have been a 6 as well. So it's somewhere there, as you have seen around the 6 generally. Anyone would like to do a very brief comment from those 7s there? Just to praise or whatever. Tomasz, you gave a 7. Very briefly.
Okay, so it was also just around 6. My partial grades were 1.8, 2, and 2. So in the end, it was 7, slightly above 6.5. I think well, one point which I was really missing is the question is the properties of the lens and the whole. And this was not mentioned there, and also in the opposition, that the lens is not only high-quality lenses, therefore we don't have to study other properties. And I think you touched this slightly more than the other teams, so just pointing out what was the real task to do, also to study the properties of the lens, and the focal length is not the only property which could influence that.
Okay, thank you very much, Tomasz. Thank all of you, also for patience. We had a few technical problems, as you probably noticed, but we managed it, and let's have a 10 minutes break again.